Okay, today we are looking at simple linear regression, and this is an extension of the correlations that we did last week, where we looked at the relationship between um, continuous level variables. And with simple linear regression, we're going to be looking at not only the relationship between two continuous level variables, but we're actually going to use one of those variables to predict the value of the other variable. That is to say, if I'm looking at age and income, like we are, can I, with any sort of certainty, predict someone's income based on someone's age? If I have their age, can I predict their income? And one thing you might notice off of the bat here is that I'm not using the WVS sample demo data, and the reason for that is a couple of things. The first is that it was really difficult to find true continuous level variables that would really truly go together. It's obviously full of scales, which are great, and you can use regressions for scales, but to represent it visually on charts and graphs, it's going to be really nice to look at bona fide continuous level variables, because you'll probably see when you run it in SPSS with the survey data, where you have scale 1 to 10 or 1 to 5 or whatever it is. You'll just pull up a scatter plot with it'll look like a square with every dot filled in, or a rectangle, and you won't get to see what the best fit line actually looks like. At any rate, there's that, and there was also a problem I had with finding data that was getting anywhere close to meeting the assumptions that we need for a regression. And for that reason, I decided to create some of my own fictitious data. Speaking of assumptions, I haven't spoke much about that at all in my videos, and we're not going to go super deep into it, but we are going to talk about it a little bit more in this video, and to just kind of quickly go through some of the assumptions that we need to meet for our regression analysis to be meaningful. We need a sample size that's at least 20, and obviously the more people we have, the more data we have, the greater our predictive calculation is going to be. We are making the assumption of a normal distribution. So for both variables that we're looking at, they should have that normal bell-shaped curve, and we can look at that a little bit later. We are assuming a linear relationship between variables, and that just means that when we plot the data, that the relationship, we plot one data, one variable on the x-axis, one on the y-axis. There's going to be a line that can represent the relationship between those data, and this is opposed to data that has no relationship, linear or otherwise, or data that might have a different sort of relationship that looks like an ellipse or a bell shape sort of thing, or a reverse of a bell shape. We want a line. So that means that as one variable goes up, the other variable goes up at all points, or when one variable goes up, the other variable goes down, and we can represent it by a line. And the final assumption, and this may not be exhaustive, but the final one I have for you is the assumption of homoscedasticity, and this is the homogeneity of the spread of the data. So at every level of your predictor variable, the spread of data in the outcome variable is going to be relatively the same. And if you're confused, we're going to go a little bit farther into this with some of these here. So the first thing that we're going to do is actually chart our data, and I think that this is useful specifically for our regression analysis, so we can really kind of visualize what the relationship looks like and what a regression really means before we plug in the numbers and look at the numbers. I think it's helpful to actually take a look at it. So we're going to go up to Chart Builder, and we're going to create a scatter plot. And so we go down here, we click Scatter, and the first one we'll do. And our predictor variable today is going to be our age, and our outcome variable is going to be our annual income. And we put that in the y-axis, excuse me. And then we're going to click OK. And what we see here is a bunch of dots that you can hopefully sort of visualize kind of a diagonal line that goes this direction through the data. And that, if we can indeed do that, that's going to represent our best fit line and our regression model. So if we double click into there, we're going to actually go through with that, and we're going to click this add fit line at total box right there, and that's going to visually represent our regression model. And we can see up here our R squared is 0.364, which means that 36% of someone's income can, or excuse me, the variance in 36% of the variance in income is represented by how old that person is. One thing I will note here, so it looks like we have a linear relationship. Things don't go up and then down. They pretty much just go up and to the right. So that's good. That meets one of our assumptions. Another one of our assumptions was we need at least 20 people. We got 30 people. Another assumption that we're going to just visually kind of look at here is homoscedasticity. And I will say that it doesn't look wonderful. I think it's probably going to be okay. But you can see that the variability in the data towards the left-hand part of the screen is a lot smaller than the variability of the data towards the right-hand part of the screen. And if that gets too extreme, if we have our dots really clustered over here and then super spread out over here, so it kind of makes like a cone shape or a cylinder or a triangle, I don't know. That's not going to be great, and it might mean that we can't use a regression analysis. And we're going to do one more assumption testing before we get into the regression analysis, and that is going to be a test of normality. And to do that, we're going to go up to, well, let's get out of this dialog box quick. Explore, and that's in descriptive statistics. And just pull over your two data points of interest. It's age and annual income. And we'll stick with descriptives there. Can click outliers as well if we want. And we're going to look at a histogram. So we click OK. And we are going to go down to this test of normality. And we want these numbers, the significance, to be above 0.05. And that is going to indicate a normal distribution. And we can see we are above 0.05 in both of the variables here. And if we visually want to look at it, we'll look at these histograms, and we can see it's not a perfect bell shape, but it's definitely something resembling one. And again with here, not a perfect bell shape, but certainly something that we could say resembles one. And one other thing we're going to look at here is these box plot, and we can see that we don't have any outliers. Again, all good news. So now we are ready to run our regression analysis. And to do that, we're going to go to Analyze. We're going to go down to Regression, and we're going to choose Linear. I'll reset this again for you guys. And we're going to put our predictor variable in our independent column, and that's going to be age. And we're going to slide over annual income over into the dependent category. And from there, we are going to go into, statistics, and we're going to click confidence interval, model fit. We'll choose that. We'll choose descriptives. For R squared and collinearity, that's something we can do in our next video when we use more than one predictor variable, but for now we'll keep that as is. We'll click continue. Plots, we are going to put our predictor in the X and our residual in the Y, and we'll look at a histogram and normal probability plot. We'll click continue, and I think that's all we're going to do for now, and we'll click OK. So the first thing that we can look at here is our means and standard deviations. So our annual income average is going to be 52,000 or around 52,000, and our average age is 36. And if we look at the correlation, we'll see that there's a large correlation between these two variables, represented by an R of 0.603. And now I'm going to scroll down to this plot right here. And this is going to tell us a little more about our homoscedasticity that we talked about earlier. Now we want this to kind of look like a rectangle, and that's going to represent normality. And you can see that things do a little bit kind of spread out the further right we get. Which means that our data definitely isn't perfect, but our data points nevertheless are spread out, and we're gonna, at least for the purposes of this video, assume that our assumption of homoscedasticity is met. And we also see that everything is within between -3 and 3, and that's gonna tell us that our assumption of outliers is met. We don't have any outliers to kind of mess up our data here. And we also want to see all of our data points follow this line. Again, not perfect, but generally we see it following that line there. And again, we see that our standard residuals between -3 and 3. So that's good news. Okay, now we're going to look at the meat of our data, which is going to be our ANOVA, our model summary, and our coefficients table. And we're going to quickly look at our ANOVA table and see that we have a significance level of P is less than 0.01, which is wonderful. I mean, we just need it to be under 0.05 like we typically do. And that's going to tell us we can indeed use age confidently as a predictor for annual income. Now, if we go up to the model summary, we'll notice that our R value here is the same thing that we had in our correlation table. And this R squared is going to be an important piece of data, because what that is going to tell us is the percentage of variability in one variable that can be, the percentage of variance in one variable that can be accounted for from the other variable, specifically how much variance of annual income can be accounted for by someone's age. And this number right here, the R squared unadjusted, is going to tell us that 36.4%, so we just moved that decimal point over, 36.4% of the variance of income can be predicted, or accounted for by age. Because we have such a small sample size, we are going to look at this adjusted R squared, and that is something that is calculated because oftentimes our regression analysis is going to overestimate the relationship between these two variables and overestimate the prediction value of one of our predictor to our outcome variable. And for that reason, we are going to stick with this adjusted adjusted R square at 0.341. So 34% of income, we can say, is predicted by someone's age. Okay, the last thing that we're going to look at here in this video is the coefficients table. And I brought over to the right-hand side of the screen here the scatter plot that we created earlier, plotting age and annual income, and also representing our best fit line here, just so you can see how these numbers correspond over to the right-hand side of the screen. The first thing we'll look at is the unstandardized coefficients. We can see that our constant value is represented by 14.1, and this is helpful for our equation. And if we were actually to use this, we want to know what we can expect a 40-year-old to make and what we can expect a 50-year-old to make. That's an important number in that regard because it's our constant for our equation. But as far as its meaning beyond that, it really doesn't mean a whole lot, because if we were to take it to its logical conclusion, this would mean that people that are 0 years old would be making $14,000 a year. Now, we know that's not correct. And perhaps we know that people that are 0 years old are making $0 an hour. And we can see that figure represented over here in this 95% confidence interval, that $0 an hour is between negative $6,000 a year and $35,000 a year. That's a pretty huge gap, but it does fall within that. What's going to be a much more useful number for us is this unstandardized coefficient for the age row, and that's represented by a 1.07. And we can see here that's our slope of our line is 1.07, and that is indeed our line, 1.07 x plus 14.11. And what that is telling us is that for every, our model is telling us that for every year increase, when every unit increase of age, and we have it represented by years, there's going to be an expected increase of $1,070 because our income is represented in thousands of dollars. And if we look over at our 95% confidence interval, we can tell that our true figure is somewhere in between $500 and $1,600, roughly speaking. And remember that, keep in mind that age is not going to account for the totality of someone's wage, but it does account for 36%. So it's important to keep that in mind when looking at this model. Another important thing to check is this significance level. We can see that that's significant, so that is great. If we look at the standardized coefficient, it's 0.603, and that is a standardized representation of our unstandardized coefficient. And it means that for every standard deviation increase in age, for every 1 standard deviation increase, we're going to see a 0.603 standard deviation increase for annual income.